Hello, you are most welcome. I'm teacher Ivan from Wuna Educational Services. You are welcome to our third lesson under heat transfer calculations. We are still looking at the rate of heat transfer in conductors. In our previous video, we looked at the factors that affect the rate of heat transfer, which were majorly three. That was the cross-sectional area of the conductor, the temperature gradient, and the nature of the material of the conductor or thermoconductivity. We shall capitalize more on temperature gradient. We saw that temperature gradient is obtained by dividing the temperature difference across the ends of the conductor by the thickness of the conductor. And therefore, from that, we shall get the definition and the units. Temperature gradient is defined as the duration of the difference in temperature between the ends of the conductor to the length of the conductor, which we take to be the thickness. So from that, we can easily derive the formula, which is temperature difference across the ends of the conductor divided by the length or thickness of the conductor. And still we can get the units, whereby since it is temperature difference over the length, the units will be Kelvin per meter. That is for temperature gradient. However, we have a question that bothers us a lot. That is, why at steady state the rate of thermal energy transfer is the same in both layers? Maybe talking about a composite conductor. That is, it's because no heat is lost to the surrounding as it flows from the inner surface to the outer surface. So during heat transfer between the layers of the material, no heat is lost to the surrounding, and therefore that maintains the rate of heat flow to be the same or to be constant. So the temperature gradient across the composite surface also remains constant, hence making the rate of heat flow remain the same. Otherwise, let us look at the calculations where we use the formula for rate of heat flow. Our number one example says an aluminum plate of cross-sectional area 300 centimeters squared and a thickness of 5 centimeters has one side maintained at 100 degrees Celsius by steam and the other side by 30 degrees Celsius. So the energy passes through the plate at a rate of 9 kilowatts. They want us to calculate the coefficient of thermoconductivity of aluminum. That is, they want us to get K. So we shall derive the formula for K from the definition. Otherwise, from the general formula of the rate of heat flow, we saw that the rate of heat flow is given by K, where K is the thermoconductivity, times the cross-sectional area A, times the temperature gradient. And from there, since we want K, we shall make K the subject, whereby K will be given by the rate of heat transfer times the length of the conductor or thickness over the product of the cross-sectional area and temperature difference. But from our question, the area was given as 300 centimeters squared, so we changed to meter squared to give us exponent -4. The length was given as 5 centimeters, which we also changed to meters to give us 5 exponent -2. The power was given to us as 9 kilowatts, which is the same as 9,000 watts. And the two temperatures were 30 degrees Celsius and 100 degrees Celsius. So if at all we substitute in our formula for thermoconductivity, we shall get 9,000, which is the rate of heat flow, times 5 exponent -2, which is the length, over 300 exponent -4, which is the cross-sectional area, times the temperature difference, which is 100 minus 30. And that gets us the thermoconductivity as 214.29 watt per meter per Kelvin. So that is how we shall always calculate by the use of the formula. Please, when carrying out calculations in physics, it is very important for you to first summarize the given information. But during the summarizing, please convert the quantities to their SI units, just like we've done. The area was given to us in centimeters squared, we converted. The length was in meters, we converted. The power or the rate of heat flow was in kilowatts, we convert to watts. So please, why are we not converting the temperatures to Kelvin? It's because the difference remains the same, whether you convert or not. Otherwise, let us go to our second example. Yes, in the second example, we are told to calculate the rate of loss of heat through a window glass of thickness 6 millimeter and area 2 meters squared. If the temperature difference between the two sides is 20 degrees Celsius and the thermoconductivity of glass is given as 0.80 watts per meter per Kelvin. So from our general equation, that is the equation of the rate of heat flow, which is K A into temperature difference over L, where K is thermoconductivity, A is cross-sectional area, this is the temperature difference over the thickness or length. However, if we summarize our information from the equation, we are given the thickness L as 6, but we shall always convert from the given unit to the SI unit, which is 6 exponent -3 meters. Then we are also given the area. Area is given already in the SI unit, so we shall just record it. We are given the temperature difference, meaning it is already a difference. So we shall just record it as 20. And then we are given the thermoconductivity of glass as 0.8 watt per meter per Kelvin. This one is already given in the correct units. So we shall substitute in our equation to get the rate of loss of heat through the window glass, whereby if we substitute and manipulate, we end up with 5.3 exponent 3 watts, or it can also be joules per second. Otherwise, we are still looking at thermoconductivity calculations. We are having more examples in our next lesson. Please subscribe and hit the bell. That is on our YouTube channel. And on Facebook and other platforms, just follow, like, share, and comment. Otherwise, I'm Teacher Ivan. I hope to get you when we meet in our next lesson.